Hello guys, welcome back to my channel. Thank you so much for tuning in. If you are new here, may you kindly subscribe to my YouTube channel, Trockers, and don't forget to also follow me on Facebook and TikTok, Trockers. Okay, so now we are moving on to yet another interesting topic, but most examinable topic, which is numerical methods. So this is more like an introduction to numerical methods, and I'm just going to go over the basics, things that you're supposed to know when we are dealing with numerical methods. Right. So let's start with the definition. Numerical methods, these are just techniques which are used to find approximate solutions to mathematical problems that cannot be solved, explicitly or exactly using algebra or even analytic methods. So we apply or we employ what we call numerical methods. Right. So remember, since it's not a direct method and we're not getting an exact solution, we are going to approximate the roots, or we approximate or we estimate the solutions. Means we are not going to get the exact solution here, right? So there are two basic methods that can be used. One, we have it's called the sign change method, and another one, it's called the graphical illustration, right? So what happens is that when you have a function, right? So if you have a function, say you have your f of x here is equal to something, right? You have your function, right? And we are told that maybe your function f of x, maybe it's ax plus b, is continuous over the range m up to n, and we want to see that it has a solution between m and n. So we are going to apply what is called the intermediate value theorem. So the intermediate value theorem is that you plug in m here, right? You get your value, then you plug in n and you get your value. So if you get a positive here and you get a negative there, since I've said this is continuous, then we can safely conclude that we have a root. Why are we saying so? So remember, guys, even if you are to graph this, right, you have your m, say your m is here and my n is there. Then if I plug in, then I get a positive here. Then I'll plug in, I'll get a negative. So what it means is, since it's continuous, the graph does not have breaks. So along the way, it has a root because it passes through the what? It passes through the x-axis. Hence, that's where our solution or root, right, or the intercept is. Therefore, we can conclude that there is a root by the intermediate value theorem, right? So when we are dealing with the intermediate value theorem, remember, if it's trigs for trigonometric functions, we have to switch our calculator mode to radians. So always remember that, right? Then for graphical illustration, so for graphical, if a continuous function here changes from positive, to that, the root exists in that interval because the function crosses the x-axis, right? That's one of the same thing here I was talking about, right? So this is the graph here. So if you draw your graph, at one point we are above here and we are below. So it means we have a root. So the good thing is the number of times the graph is going to intersect the x-axis and tells us about the number of roots. But there are certain situations where we don't have a single graph, we have just two graphs. So it means for the two graphs, suppose here you sketch your graph, your first graph here, right? It's like this. Then when you sketch another graph, it's like that, right? So these graphs here intersect twice, so it means we have two solutions. So the number of times the graph intersects and tells us about the number of what? About the number of rows. So this is, like what I've said, these are just the basics that you are supposed to know when we are dealing with numerical methods, right? Then we move on to errors, right? Remember, we are approximating, hence we are bound to make errors. So for errors now, we have three types of errors which you're supposed to know. The first one, which is the most basic one, is called the absolute error. So the absolute error is just the difference between the actual value and the estimate, right? So we always take the absolute, meaning say whether it's negative or positive, the answer will be always positive. So for example, if it's like 2 minus 4, right? We are going to get negative 2, but the error is always 2 because it's the absolute, the positive. We consider the positive, right? That's the meaning of these absolute what? Absolute signs, right? Then we have the relative error. So the relative error is just the absolute error divided by the actual measurement. So in this case, my absolute error was 2, right? And maybe my actual measurement here was 2. So it's just 2 over 2, which is just 1. So in this case, it will be 1, right? Remember, actual minus estimate is the absolute over this. So relative error is just absolute error over actual, right? Then we have what is called the percentage error. So percentage error is simply relative error multiplied by 100%, where we are saying actual minus estimate, which is our absolute, divided by actual, then times 100. Then we get our relative error, right? So guys, make sure you also know this, right? Always do justice to yourself and remember that, right? Then we are going to be dealing with, calculators more often here, especially when we do our iterations, whether we are given an iterative formula or it's the Newton-Raphson method. So you need to know how to use your calculator, right? That's your savior here, right? So when you are using your calculator, you are given an initial value, or sometimes you are asked to estimate an initial value. So for example, maybe it was just in the range 2 up to maybe 3, right? Then you ask it to estimate, the initial value. Obviously, you can consider 1.9, or you can consider 2.0, 1. I mean, it's something that is near these roots here, right? Or even something that is in between, or 2.5, whatever, as long as it's within this range, or even 3.1, right? It is going to converge to the actual root when we continue to perform successive iterations, right? The more you perform the iterations, the closer we converge to the root. So when you're using the calculator first, right, what you're going to do when you're using a calculator, first you have an initial value. So in this case, maybe my initial value here is, okay, so maybe my initial value is, let me turn this on. All right, so maybe my initial value is 0.5. That would be my initial value. So this 0.5 is now stored, right? So maybe your function is f of x. Maybe your function here is f of x. The iteration is maybe xn minus 2xn squared plus 4, right? So what you simply do, instead of continue to repeat, because we are supposed to you're supposed to use the preceding value, the preceding root. Remember, for the iterations, you've got x1, x2, x3. So to get x2, use x1. To get x3, use x2. So in order for us, to save time, once you know how to set this up, so once I say x1, this was my x0 here. To get x1, you use x0, right? So to get the next solution, you're going to estimate that. You're going to use this root. So you just come here for xn. You just say xn is just the answer. So you just press answer here, then minus 2 times, if you want, you can say times answer squared. I'm sorry, 2 times answer squared, right? Then plus 4. So this is what? This is our iterative formula that we have, right? So when in this case now, you just have to continue to press OK, right? So it's going to use the previous answer, right? Remember, this was just a generic, but the more we perform these iterations, the closer we converge to the root. So that's how we do it. Instead of, like, imagine I got this, then I have to retype using this value, but using the answer method, it's going to save us time. So that's exactly what I was explaining here. So to obtain the next root, simply press an equal sign only and write down the displayed value as it is, and then round off to the required degree of accuracy. Continue to do that up to the required root, right? So you only press once. If you press twice, you're going to skip a solution, right? So literally, We are going to do the same thing when we do our Newton-Raphson method here. You know the formula for Newton-Raphson, which is xn plus 1 equal to xn minus, then this is our function of xn over the first derivative of xn, right? But xn will be the initial, that's the solution, the first solution that you have, right? Then you keep substituting, those new solutions that you get, your x1, your x2, your x3, your x4. Because remember, the formula will be like xn plus 1 is equal to maybe xn minus something, right? So to get x, if you are given the initial is x0, so to get x1, it's going to be x0 plus 1, meaning say it's now x0 plus something something. Meaning say we are going to get x1, we're going to use x0. To get x2 here, it's going to be x1 plus 1, which is equal to x1 plus something. So instead of us continue to plug in this calculator value, because sometimes it will be, a very, large number. But once you save it in the calculator, it's going to use the previous memory. That's the good thing about that, right? Then there's also one thing that you need to understand, guys, when we are solving problems on the trapezium rule. So remember, for trapezium rule, you need to know when it gives an overestimate or an underestimate solution, right? So remember that we get an overestimate when the curve is concave, and we get an underestimate when the curve is when it concaves down, right? Here, when it concaves up, that's when you get an overestimate. And now I will explain why. So in this case, that's a concave down. But remember, for the trapezia, right? The trapezia here, suppose it's like that. Right? These are straight lines, guys. Sorry, I have to connect the endpoints here. But remember, if it's like this, if it's a curve like that, means say we have this unutilized space here, hence it's an underestimate, right? It's an underestimate. So we get an underestimate when we have a concave down, right? Then also, if we have like a concave up situation like this here, remember maybe your first ordinate is here, another one is there, another one is here. So when trying to connect, remember these are straight line, but there is an overlap because we don't need this information. Hence, you're going to get an overestimate. We are going to get an overestimate. So you need to understand when we get this overestimate and when we get an underestimate. So now, in the next videos, we are going to see how we do the actual iterations, including the Newton-Raphson, as well as solving problems on trapezium rule. But also you need to gear yourself up on your graph sketching. You need to know the parent graphs, the parent function graphs, such as x squared, x cubed, function of x is equal to x, absolute of x, square root of x, e to the x, ln x. Those, you need to know those basic graphs, so that when you do your and even 1 over x, so that when you do your transformations, sometimes you just apply your transformations to these graphs, then you take note of the key features, right? So I will see you in the next segment, guys. Thank you.